Mostly a physics talk with a lot of hand waving and intuitive ideas. And hopefully I will be able to convince you something. And some of these things which I am telling in hand waving can be actually shown. But I am not going to try that because it will take a lot of simple calculations to be repeated. So this is based on several pieces of work, and then I have assembled some of them here. So this is the plan because I want to understand on-commutative spaces with the boundaries. Now it's a very tricky question. We don't even understand that at the commutative level in some sense, but there it has much better in an operational sense, but at least there we have some good understanding. So I want to extend that to non-commutative setting also. So I'm going to use it in this kind of a simple models at the end of the day. Why is it we are interested is, well, I started some of these works to, can I think of black hole horizon as a boundary? That is the kind of questions. And can I somehow associate some of the things which are happening in black hole apart from the major dynamics and other issues taking place in terms of something happening on the boundary. That is a motivation. And there are other issues where we were interested earlier in quantum Hall effect or several things which with Ball and others were doing, something happening at the boundary even though the dynamics doesn't know anything about it internally. So that can also be, can it be understood? Now many of these things turned out to be, have some relation to even some models with non-commutative spaces, so I'm going to extend that to these cases also. And the final punchline is something which is not listed here as a thing, but I have written up in this. Okay, I'm going to start. Unfortunately, the picture is not clear. I have to tell you who are these people. And this is Dirac, this is Bose, and this lady is was a student of Bose by name Purnima Sinha, and her daughter is my friend who is in Raman Research Institute. Probably Bal and Sachin also know. She's Suparna Sinha. Okay, so the interesting thing about this picture is Bose is representing bosonic statistics and Dirac is representing fermionic statistics, and there is something in between. And what I'm going to tell is also motivated by this picture that in non-commutative geometry typically or generically is a fermion is less of a fermion, a boson is less of a boson. The statistics changes to some extent, and can it be made at the observational level where something where we can play with that? That is the question, and that's why I'm interested in this. And the two places where I'm going to remark that it actually can probably play a role, and that uses in one case fermions, in the other case bosons. Now with reference to fermions, this thing is, I will tell you where that I'm going to use it beforehand. With respect to fermions, the basic idea where it is used in astrophysics is the question of white dwarfs. Now what happens is you have gravity, the electrons are there, electronic pressure, and there is no other thing. There is nothing, there is no nuclear force, everything is over. And what happens is there is a gravitational pull of all the electrons and also matter which is there, and there is an electronic repulsion due to electronic coming entirely from Pauli's exclusion principle. Now these two balance, and the whole idea was worked out several years back, several decades back by Chandrasekhar. He said that 1.5 solar masses is the limit, and we won't be able to go beyond that. Now we would have been happy if that was the case, and it was verified to some large extent at that time, even after that. Unfortunately, my friend Bani Pratap tells me there are now examples with 2 solar masses and things like that. How is it violating? So is there a violation of fermionic, this exclusion principle? Can it help at that level is the question. And some model which I am trying to mention here later at the end of the day may help. That is the point. And second thing is about the bosonic thing. What do you do with the bosonic statistics is you form the Bose-Einstein condensate. Okay, Bose-Einstein condensate is going to give me some kind of a lump, which is all the bosons go and sit there at a particular temperature, critical temperature, if it is satisfying, and the density is such that you can form a statistic. Now, can it happen in any of the cases? And one of the model, in fact, yesterday somebody was, speaker was talking about, probably you were talking about dark matter candidate, which was, unfortunately, your candidate was a fermion, my candidate is a boson. Okay, my candidate is, which probably I will talk in detail about that in the next conference here itself, which is about, can photon be massless? Should photon be massless? The answer is, you will find that if the mass is very, very tiny and small, okay, it can actually be, nothing will happen. To all our experiments we have done so far, it's a transverse degrees of freedom of the photon will be visible, and in all the interactions, nothing will go wrong, and you will be completely happy. But there is an extra degree of freedom when it is massless, and that is like a Stuckelberg field in the sense of the term, which is there, which is like a scalar field, and it's like a boson, and it is massless. The only thing it does is gravitational interaction, because it doesn't interact with anything. So if it has bosons, and this thing, the only thing it can do is bosons. The question is, can it be a dark matter candidate? Now, I would have left it several years back, because many people said that relic density requires the mass of the dark matter candidate should be above keV. But the mass which I am going to give is, as per the limits which are there, is 10 to the power minus 20 electron volt. His dark matter candidate is 10 power 8 GeV. My candidate is 10 power minus 20 electron volt. Now, can it form? Well, there was a great phenomenologist by the name Edward Witten. He wrote a couple of papers last couple of years back, where can ultra-light dark matter be a candidate for dark matter? Answer is yes, it can be, because of the circumstances that the ultra-light dark matter, like axion, in that he was looking at, it can be a dark matter, provided there is a density such that you are able to form a Bose-Einstein condensate. Now, if you are forming Bose-Einstein condensate, and if the densities are quite high of this type, then that will also be affected by non-commutative geometry if it is present. So, in both the cases, there will be some changes, and I want to explore as a conjecture towards the end. Before that, I will try to explain what is going to happen in many other ways. So, why is it we are interested in manifolds with boundary? So, the quantum physics on Riemannian manifolds with boundary exhibit novel phenomena, new phenomena, and even in commutative geometric framework, there is a physical need to understand them. We know the boundary is dangerous. At least we know that in our case when we go near the border between India and Pakistan, that you may survive or may not survive depend on where you are. Okay, so this is the kind of thing, but it has several uses, and quantum black holes, edge states in quantum Hall effect, topological insulators, etc. Now the interesting thing is, because now we expect that non-commutative geometry may be required, space-time geometry may be quantum space-time, then you will ask the question whether there is some effect of some of this. Interplay between non-commutativity and boundary effects, I am going to explain in some simple examples. In addition to such a study, the fact that several situations like quantum Hall effect or nearer horizon geometry, we need to understand quantum space-time in some context, because the quantum effects can be substantial in this case, but here the quantum Hall effect, it is the effect of the boundary itself, but there is a magnetic field which provides some kind of a new geometric setting where this kind of a thing will be there. Now the two understandings which I have mentioned here is Chandrasekhar limit and Bose-Einstein condensate. Hopefully I will mention few more things about it. So this is ideas come from Riemann himself. By the role of non-commutative geometries, he didn't talk about non-commutative geometry, but I was told of these things by Sergio Doppler. Now, and the requirement of quantum level, you need some kind of changes in geometry. And this is the thing, I started looking at near horizon geometry of black holes, and also there are a lot of things about Big Bang singularity and cosmological constant by Steinaker, and several other people have also looked into where are the situations where some of these things can be useful. There is need to go beyond the conventional notions of geometry was anticipated by none other than Riemann himself, given the lack of knowledge of physics at infinitesimal length scales. This is a very interesting quote which I saw in Riemann's habilitation lecture, which is saying the metric relations of space in the infinitely small do not conform to the hypothesis of geometry, and we ought in fact to suppose it. We can thereby obtain a simpler explanation of the phenomenon. So this is basically the thing that I have to postulate. At the infinitesimal scale, something new is going to happen, because the physics of the scale by which you are measuring any length is also involved in the game. So you better be careful about that. This is the kind of thing which he was trying to pose. Unfortunately, he was very profound, but he didn't have beyond that to say anything, which is very interesting. So now I am going to look at what happens even in the conventional thing, which the last lecture there was a lot of discussion about the boundary conditions which were required, and I am going to focus some of those things, what happens at that stage. Now, when you go to Riemann in manifolds with boundary, generally we are interested momentum square operator minus del square, or a Laplace-Beltrami operator. The question is, if it is manifold with boundary and we want the space of square integrable functions in this manifold, the theory of spaces deficiency indices of von Neumann is a framework in which we answer this question. So we will find that there is plus I eigenvalue and minus I eigenvalue deficiency spaces. If they are equal in size or unequal in size will determine whether it is self-adjoint, or whether it can be made self-adjoint by suitable boundary conditions, etc. will be determined by that. So what will happen is Laplace-Beltrami operator on these manifolds, when you try to do that, there is something interesting. If it is one dimension like the interval 0 to 1, I can easily do the calculations and boundary thing, etc. and find out how many, what are the boundary conditions allowed in this case. That's what I can do. Can it be parameterized by one parameter? That's the question. Answer in 0 to 1 is, you will find that it is easy to answer some of those questions. Now when I go to something more, like a disk or like a ball, okay, what are the, or some manifolds with boundary, what are the boundary conditions? Is better we do not, because the deficiency indices in those cases are infinity, and there is no way I can answer what are the boundary conditions which are suitable for that case. So what we are going to do is we are looking for this thing where the domain of del square and the dagger of that in the domain both should be equal. So the answer was given by Azori about Marmot in one of the interesting papers maybe a decade back. And the thing is this thing, you have boundary conditions. You have a value of the function, scalar field in this case, on the boundary, and there is a normal derivative. You form the combination phi on the boundary minus I times the normal derivative, and then you form plus I normal derivative. These two conditions are related by a unitary matrix. So that unitary matrix will determine the boundary conditions, and this will automatically ensure these boundary conditions that the operator is self-adjoint. Now when u is plus 1 or minus 1, they will correspond to the conventional thing which we teach all our students in at least physics classes, where electrodynamics is taught. We will say Neumann boundary condition or Dirichlet boundary condition. So they are the two limits which are here. But in principle, this allows all sorts of boundary conditions which are there. Even in the case of what we do in conventional quantum physics class, introductory particle in a box, which is something like 0 to 1 interval. If I am looking for momentum square operator, Hamiltonian, minus del square minus d square by dx square, if I am asking, it is given by a u2 worth of boundary conditions which are there. So given that kind of a situation, we have a lot of them, and we are going to study a specific set of them, which is useful, because in the examples I am going to have, the manifold have rotational invariance. I am going to put those conditions of rotational invariance also into the picture and look for what is going to happen. Why is it? This motivation comes entirely from physics. So the physics is something is happening at the boundary of a black hole. Can I understand that? To some extent, or something is happening at the boundary of a quantum Hall disk, or some kind of a topological insulator on the boundary itself. So can we understand some of those things without the details which are required for our problem? So this is the thing. One of the interesting feature is possible existence of edge states localized close to the boundary with negative eigenvalue for minus del square. Minus del square is a positive definite operator in a conventional R3 or some of these, or this case, but in these cases with these boundary conditions, there is a possibility of bound states localized on the boundary and living only on the boundary. If you have a ball, it is like a water on surface of the water ball. It's like on the earth, it's like the ocean which is there. Some kind of bound states which are there on the boundary. So that is the thing which is negative eigenvalue, localized in the sense that if I find the expectation value of that state with respect to position or thing, you will find that will be completely localized as in a thin shield. Now this is actually very interesting. This kind of eigenvalues for this thing was well known earlier in several domes which are there, where they have a thing that somebody speaks or something in one end of the dome, it is audible at the other end, but nothing in between. What happens is these modes go around, okay, the whispering gallery, they go around, but they don't come inside. So this is the kind of a thing modes which we are looking for, completely localized on the boundary. Okay, so to appreciate, I'm going to, so what is done is some kind of a collar neighborhood, and outside is the so-called bulk. The contribution of the bulk is always positive, where we don't care, and we are going to worry only about what is happening in the bound, in the collar. So what I'm going to do is simple example. For simple example is, I'm going to have, instead of one dimension, I'm going to take 2 dimensions. I can do it in 3 dimensions. And very interestingly, that whatever I'm looking for is happening here itself. So what is happening is, I'm taking R2 and I'm removing a disk. I'm removing a disk. Why is it I'm removing a disk? I just want to picture at the end of the day, my black hole or something with horizon is in the space of R3, something here, or even some manifold, that some object like star, which is nothing is coming out of it, you don't know anything about what is happening inside. So it is out of your boundary, outside your scheme of thing. So essentially remove it and see what is going to happen. So this is basically the idea, R2 minus disk, and I'm going to look for a boundary condition. If I use that, I'm using this boundary condition which is called Robin boundary condition. It is interplay between Dirichlet and Neumann boundary condition with a parameter which is kappa here. So this is an interesting thing. This is rotationally invariant boundary condition. In principle, there are much more than that. There are some more rotationally invariant which are not interesting. So I'm focusing on this. Okay, so this is the problem I'm going to solve with this boundary condition which is there. Okay. Now this kappa which I have written down, this dr is 1 by r there. So the kappa which I have has length dimension of 1 over length inverse. Okay, so that's the first interesting point. That length dimension which you have introduced in your theory was not there in the previous thing, and now you have introduced because your dynamics somewhere demands that there is some thing, etc. Now where can it come from? If I am considering a metal, or if I am considering quantum geometry quantum space-time, etc. So if I'm considering my metal, metal is consisting of various atoms on the surface. So this is not a continuous object. Any material is not continuous, but it is made up of atoms with some interatomic distances. So there are some characteristic length scales which are there even in metals or any of these things. Or if I am taking a quantum space-time, there is a characteristic length scale even there which is given by Planck length. So there is a fundamental length which is there at the end of the day which is required if I am looking at the thing as a quantum geometric problem. So given this, I can ask the question, if I solve this, what happens there? Now, as I mentioned earlier, there are bound states. On the bound states, this is simply the explanation of how to solve the problem. I'm essentially putting the solution in this thing and then writing down the radial equation and solving this with the boundary conditions which are there. And the solutions are Bessel's function of modified Bessel function of third kind or something like that is what is we always teach in mathematical physics courses, and that is the Kn which is there. So this is the solution. The other solution, In, is not a solution because it will blow up at infinity, but this is the only solution. And I have to solve this equation with a fixed value of k. The value of lambda here, the eigenvalue, is to be found out, which satisfies this equation. So I've tried to find out for different values of n. I start with 0, I start next 1, 2, 3, I go on and find out the value of lambda at every case, solving that equation. And I find, very interestingly, beyond a value of n, n max, there are no solutions. There is no lambda which will satisfy that equation. And that is what is the interesting thing. And I easily can point out what is happening here by, I don't know whether this graph is there. This first line here is for n is equal to 0, 1, 2, 3, 4. And if say kappa is 10, beyond the value of that 10 or something, some number here, you will not find any solution because all of them are monotonic and go down like this. So if the function on the right hand side is not going to cut this thing, there will not be any solution. And all the solutions are maximum value is this thing. The number of solutions, very interestingly, I told you kappa has the dimensions of length inverse. Now we have another radius which is given by the radius of the disk itself. So the product of them is a number. It may not be an integer. You take the closest integer, largest integer contained there, and that is the maximum number of solutions for this problem. Now it is interesting from one point of view. It is interesting because there are exactly the number of bound states, which I call edge states, are proportional to the radius, or you can say proportional to the circumference of the circle. Now if I extend this problem through a ball, if I do that in a ball, okay, then it is proportional to the area. So how many bound states that will be there on the surface is exactly proportional to area, and from there I should be able to link up to the generic phenomenon that the black hole entropy which you have, the microstates which you count, is proportional to the area from this itself. So this is basically the idea. That's why I was motivated in this. It so happened I was talking to Michael Berry and about this result. He was excited and he said I should pursue it. So I did pursue it to this extent. So this is basically the R2 minus disk, or disk if you want to have, and what happens in the commutative case. Now if I want to do the same thing in a non-commutative setting, I should somehow, first condition is I should somehow, whatever I am getting in commutative limit, I should be able to go to. That is at least my minimal motivation which are there. Okay, with that thing, I'm going to do the review of fuzzy disk, a brief review, which is essentially I'm going to use a Moyal case here, but this is generally R2, but I'm going to put the boundary conditions following some of the earlier results. Then I will tell you that is not sufficient. We have to go beyond that, and those conditions which I'm going to include will be more than that. So I would like earlier our Sachin was explaining, these are the things which are used. and then Moyal plane is described by some kind of functions like this z and z bar, where z is, I should have used a and a bar, okay, a and a dagger, and this is the kind of functions which are there, or algebra functions. And then we have everything here, and the functions. The reason why I'm using this kind of a thing is because this is explicitly giving in terms of what is known as the coherent state representation of harmonic oscillator, and I can go to the commutative limit from this better than the other. So it is easier to do. The commutative limit is easier in this picture, and that is what I am using here. Okay, so the continued review. So this is the kind of various functions which are there for arbitrary function, and this is the, we have set up the machinery required for Moyal plane from the where the fuzzy disk should be carved out. We have the Moyal plane, I have to carve out the fuzzy disk to achieve our thing. So for that I am going to use Fedele's trick to tell, at least as a starting point, and this is the thing which was there, that there is a projection operator which is up to 1 to n, 0 to n, and that is a projection operator of the functions which are going to be used, and that is a trick which was used to describe our fuzzy disk. The class of functions which are used are using the projection operator, and the various things are easily worked out by looking at this p theta n which is there in this form. Okay, now this incomplete gamma function in the limit n tending to infinity, theta tending to 0 with n theta is equal to r square gives a subclass of functions on disk. But this subclass of functions, you will find that obeys only Dirichlet boundary condition. It has only Dirichlet boundary conditions, but I know my disk has other functions, and those other functions are required if I want to understand even the self-adjointness of minus del square. So what is it I can do? And the first thing I can do is look at what is the derivative, because I need normal derivative. So I am looking at the derivative, and then eigenvalue equation I am writing down, and the condition which is required for satisfying the Dirichlet boundary condition is this Jn Kr is equal to 0, and then you write down the functions which obey the Dirichlet boundary conditions within this scheme of things. Okay, so the Robin boundary condition is simple, that I have just extended to obey this set of boundary condition, that Jn Kr plus this thing, and then try to solve the problem. Okay, so now we have, as I told you earlier, there are positive k-square solutions which will be there always, but k-square negative solutions will also come out. So they satisfy this required, instead of Jn, they satisfy In, because I am doing within the disk. In the earlier problem I did outside the disk, inside the problem that In will come, and that's what I am writing down here. Now they are finite in number with n less than n max, and this maximum value is quite stable. It is there for large class of things which are there here within this thing, and what I can do is I can plot, for example, with positive energy, these are the solutions which will be there, which will look like Dirichlet boundary conditions, and with again positive energy, but the negative energy solutions will look like this. Okay, now they are all, so I have a disk, they are localized at the boundary. They are localized at the boundary, and that is this set of solution. This will actually blow up, but only thing which I am looking for is the blue solution, fuzzy solution, which is here, which is my, what you may call as the Robin boundary condition solutions, if I change it to this thing. So if I include this class of solutions also in this earlier set and consider them, then this problem come with the idea that in the commutative limit, if I take the same commutative limit, it will describe my quantum mechanical problem, which I will get out of minus del square operator with suitable boundary condition. For achieving this kind of a thing, I have to do this extension. Okay, now we can truncate the series using projectors, etc. But I'm going to do slightly different one, because I asked the question, how do I get the boundary? How do I get the boundary? In quantum Hall effect or even in black hole, etc. The boundary is some potential, some infinite potential delta function kind of potential which is created on the boundary. For example, if I want to do quantum Hall effect, what they do in the actual experiment is they create a potential well, so that the electrons are going to stay only in that. Okay, it's like a potential well, very deep potential well, and the electrons stay in the two-dimensional plane, and that is how it is achieved. So similar thing is there for any other problem. So I'm going to do, in the non-commutative case, a potential well. What is the potential well I should create? I should create a potential well around the disk. It is delta r minus r in the commutative limit. But in the non-commutative case, it will not be like that. It is a coarse-grained version of that, and that's what I'm going to explain. This work was done by Scholz and probably Sachin here, and Biswajit was also involved, several people, and this is the kind of a thing, and I'm going to mention what is done there. Okay, for achieving this, I'm going to do a potential well in Moyal plane. I can easily go to the commutative limit from this. In fact, you will find it so surprising. The condition which I'm getting is identical even in the commutative case. So this is the thing. So this is the projector from n to n plus m. So I have a potential well between n and n plus m, and from 0 to n, potential is constant, nothing happening, no potential. Outside m, there is nothing, and there is an infinite well, like a moat outside a palace. So that is what is there, and the well is here. I have written this 0 to n by this number, n to m, this is that other number, and m to infinity another number here. So this is actually 0, and this is 0, and this is some value is what I have for my problem. In the limit n tending to infinity, theta going to 0 such that n theta is equal to r square, you will find that this Vnm here will become a delta function, and Vn is equal to 0, this is 0, and that's what is the thing which is there. We solve the equations. So what is it I have to do? I have to solve the same problem. I have to solve the Moyal problem in the three regions and match the boundary conditions. And this is what is a Moyal plane non-commutative potential well. In the Moyal plane is this, second is the only thing which is there, and I have pictorially represented it because my problem is the functions which I am using are rotationally invariant. I am using this simple diagram, heuristic picture for the Moyal plane. Now I can write down the solutions for different regions. They are given by this L, N, M functions and U functions, which are known as associated logger polynomials and Kummer functions, and they go to the limit of Bessel functions in the appropriate kind. Thank you. I'll finish it. So one needs to match the boundary conditions, and this is what you have here. Okay, I will not go into the details of this. This is what is the boundary condition reflection, and the limit of this thing is exactly this condition. This condition was given in our earlier paper in the commutative disk with the delta function potential. It's exactly this condition, which is a condition between the Bessel function of Im and Km. They should obey this thing, where the G here is product of the theta times V, which is there. In the earlier case, it is potential V times delta function, constant which is there, depth of the potential well will come. So this is exactly the thing, and the number of bound states is constant over small values of theta. Even the bound states for small values of theta, it doesn't change. It gives you the same number of things because of this situation that there is always that bound states which are localized, whether it is commutative or non-commutative, the number remains more or less a constant, unless there is a transition to the next level. So this is the interesting thing which is there in this problem. Okay, now this, unfortunately, this kind of a disk is not completely useful in my opinion, and if I want to use this kind of an idea for say white dwarf, which I want to label by this, I have to go beyond that. And in order to go beyond that, I use the previous lecture's introduction to what I wanted, which is the squashed. He had fuzzy sphere. I'm going to squash it so that it becomes almost a disk here, with the equatorial plane as the boundary of the disk. So what is the thing is, what is required, my astrophysics friend always was telling me, is I should have non-commutativity, which is at the core, which is very high, and at the boundary it should be much small. So I should get that kind of a changed situation, and how do I get is the question. So this idea is what I'm going to use. The work I'm using is the work by Steinacher, which is fuzzy spheres, natural candidate, and this is the fuzzy sphere thing which he wrote, and I'll explain what is the squashed fuzzy sphere directly, because I have only 5, maybe 7 minutes. So this is the sphere, and I'm going to squash it, which means I'm going to replace by x3 by the x1 and x2 with this condition, and my Poisson structure on the plane turns out to be this when I do the projection, and this is the projection with some lambda parameter here, which is coming from that R and the constants which are there. So this is a fuzzy, squashed fuzzy sphere, and the eigenspectrum of this can also be easily found out. It is there, and we have to use it for the case of finding density of particles which are there to match our kind of requirement. So this is the thing, and you can easily see it correct has interesting outcome is, this is something like an effective magnetic field. The effective magnetic field varies at the edge, and we reach almost commutative space, and inside at the core it is very high. So this is a kind of a situation which is useful for us, and this is the kind of discussions I have been having with Bani Pratap, who is here. He may also talk more about some of his work. Okay, so now this I am going to skip, which is since I don't have time, I can do the same thing in 2+1 dimensional solitons, which is some work which we did earlier, but the only thing is we can do it in the disk also, fuzzy disk, which is very interesting, which is related to what Bal was talking today morning, which is like a cylinder with theta coordinate and t coordinate, and there are solitons in the non-commutative case, which is interesting, which I will skip now. Okay, now BTC deformations are not required. Now the last one, which I didn't write it here, is about the so-called Bose-Einstein condensate, which I didn't write. I didn't have time to write it up. I will mention what is being talked about. Is if I want to talk about a theory of photons, electrodynamics of photons with electromagnetic field, but I want to make it massive. This question is not my question. It was asked by Schrödinger about some 50 years back. Should the photon be massless? That's the question he asked. The answer was very clear, that where will you go wrong if I introduce a very small mass? And he said, he computed everything which was there, that mass terms don't play any role if I keep a very, very tiny mass in all the calculations. In fact, it saved one other problem. There was a problem of infrared divergence, and that was solved by introducing this as a parameter. I don't know whether that parameter is non-zero or zero, and Schrödinger himself estimated the value of that mass, and by using the Earth's magnetic field over a distance, he found out that the mass of the photon should be less than 10 to the power minus 16 electron volt. 10 power minus 16 electron volt. For your comparison, I can tell you electron itself has a mass of 0.5 MeV, and all the neutrinos which people talk about here in these cases are less than electron volt, but of the order of 0.1, 0.5 kind of thing, and all other things are much more. For example, 936 MeV is for the proton mass. So the mass which I am talking about is 10 power minus 16 electron volts. People have improved that technology to find the magnetic field of Earth's magnetic field over a region and increase the bound to be less than 10 power minus 18 or 19 electron volt. So typically, if you take the scale, if you take the particle data book now, it gives you a limit. The photon mass is less than 10 power minus 18 electron volt is what is given there. If you take that as a case, you can now ask the question, Can it be a dark matter candidate because it doesn't do anything except gravitational interaction? Okay, answer is, then how is it possible? Then cosmological questions will come, and the cosmological questions require that kind of trick like what many people have been recently talking about, that they should form a Bose-Einstein condensate. For that, it should be a boson, and it is a boson as far as we are concerned, but because of the effects which are there, the density of these things can be comparable, and this thing, there could be a coherent effect, that there may be corrections to that from quantum gravity or whatever effects which are there. Given that, because the parameter is Planck length, but the number is multiplied by some number n because of the densities, etc. So based on this thing, if they form a Bose-Einstein condensate, it can help in the sense of producing correct what is known as the rotational curve equation for the dark matter candidate. And this is the basic idea, and if such a solution is there, now that solution which was worked out does not use non-commutative geometry. It uses only commutative thing. But if I introduce corrections which are there, you may find that it is helped, because you will have a Bose-Einstein condensate formed by less number of photons, because Bose-Einstein condensate will require a critical density. The density will be lowered. In the case of fermions, there will be more fermions at the center because fermionic repulsion is less. Now in this case, the bosons which try to be together is going to be less of a boson, which means they will go apart, so the density will be less. So in both cases, some role will be there for these two things, and they will have an effect, and I am trying to estimate both these things in various calculations. So that is where I am as of now, and several papers are there, and some more papers which are being written up as of now, and the last two things are being mentioned here are there. And already there are one more paper which I didn't mention is already appeared in the journals. Thank you very much.